Well, first of all, let me just show you this. This is the robot we're all talking about. Here it is, right there. This is our surgical robot. It's called Mira. So I am a faculty. I'm a professor of engineering at University of Nebraska, but I'm also co-founder of a company called Virtual Incision that's developing this for clinical use. So the first thing that's incredibly different about this than all other robotic systems is that it's very small. Robotic surgery systems out there are very large. They can be up to 9 feet tall and they weigh about 2,000 pounds. So it's a much, much different approach than this. What's similar with them all is that they all have a console. So in some ways, the surgeon is remote from the patient. They use this to control the device. The robot really doesn't do surgery. The robot does exactly what the surgeon tells it to do. And the surgeon will sit across the room at a console and control the robot somewhat remote. What we've done here in this experiment is we've made it very remote by putting the robot on the International Space Station. So that's just the basics. The last thing I'll point out is that there's a camera, laparoscopic camera. The device is made like you and I are made. You got a right hand and you got a left hand. You have 2 arms, and then you have this camera like your head that looks around left, right, and down. And that's like we've shrunk the surgeon down and put them inside the patient. So when they do what's called laparoscopic surgery, they actually inflate you. And it's like putting a salad bowl on your belly. It lifts your abdominal wall up. And there's kind of that much space in there. We put the robot inside your body. So everything below my hands goes inside the body. And then the surgeon can do surgery. Does that basic idea make sense? Any questions about that? We're going to have a small group so you ask questions as we go. What's exciting? Well, what's very exciting is we just February 23rd received FDA marketing authorization. So we're just now beginning to bring our product to market, and we hope to be doing surgeries in a few hospitals before the end of this year. So it's a very exciting time for us. You'll notice some of Rachel's dates around February too. We had a very busy month of February with our space station flight and FDA approval. I always have to point out that the application was 35,000 pages. It took a while to put the application together and a lot of effort there. And we did a 30-patient clinical trial as part of that too. Quite well. The robot is waterproof. This doesn't mean much to some folks, but almost everything in the operating room is covered with drapes. And so there's a plastic barrier between sterile environment of surgery and other objects. Not with our device. It's sterilized and used just like this. So you can wash it under a sink after it's used, and actually the robot is designed to be used 15 times, 5 times. So anyway, we made a funny video just to show that it's sterilized. The fish are very easy to catch, and we didn't harm any fish, and we did the video. Our robot's really strong. Some people ask about the small size. It's still very, very strong. You need some strength to close hernia go to move colon around and things like that inside the body. So we took a version of this as with my class on small robots for surgery. And I'm interested in our work because both the Army and NASA want to do surgery in crazy places. Almost all soldiers die in the first half hour after injury or golden hour. Sometimes they stretch it too, but you need to get surgical care to soldiers very, very quickly. And if you can do that remotely with a surgeon at a remote site, I think there's potential there. So NASA came to us and asked if we actually gave us a grant to fly in the International Space Station, sort of as a capstone of all of our research. So Rachel talked a little bit about pre-launch testing, and she showed this experiment locker. This is about the size of a microwave. It's kind of this big-ish. It's upstairs. Everybody needs to go up and see it. Space Mira, and so this robot and this box are upstairs. Everybody needs to go check those out. But they connected power and Ethernet, and then they really just flipped our switch on. And that's really all we asked them to prove. And there was a question earlier. This was really just a technology demonstration. It's the first step to show what's possible. If you're thinking about surgery in space, things have gone very, very poorly. You're in a tough spot. That's kind of down the road further. But it's something that's going to have to be thought of because, return from low Earth orbit can be reasonably quick, but not from Mars and not from the Moon and not from asteroids. So as NASA plans to go further out, this kind of thing will be more and more important. So Rachel on the right, some other students there. Rachel kind of described all the testing that was performed. Launch is fun. It's just my policy that if you have a picture of a rocket launching your robot to space, you should play that video every time. So I will just because. But we got to go down and see the launch. And that first stage of Falcon 9 coming back is as spectacular as you see it. This will be back to the landing site to land. Sometimes they land out on the drone ships. It's pretty spectacular. As Rachel mentioned, we were on the Cygnus Northrop Grumman cargo ship. So it takes a couple days to get to the space station, but here it is arriving at the space station. And then the device was installed. So there's our microwave-sized box. And again, that's astronaut Laurel, expert on flight. So today, Canadarm, she's the Canadarm expert there. But she's sliding our box into this express rack. Kind of a holdover from the space shuttle days. It's just kind of a standard box. So she installed that before. So you can see the yellow and red connectors where she will install the power and video. Then we had her check a few connections. So she took her flashlight and looked around to make sure everything was connected. And let me just say, I shouldn't act surprised. Everything worked perfectly on this flight. Everything was fantastic. Nothing was broken. And I don't really, again, I shouldn't act surprised. As soon as she did that, she turned it on. And the robot, as Rachel mentioned, went through a pre-programmed path. So we'd actually cut some rubber bands on Earth, we recorded that path, and we redid that on the space station. So the video on your right is actually happening on the space station on, I don't know, February 6th or something like that this year, not too long ago. But you can see, we call it simulated surgical tissue, but they're rubber bands, right? And an act of surgery that's very common is you grab tissue, you retract it to provide tension, and then you perform a dissection of that tissue. And so that's what's happening here. You can also see how their cameras moving around so that you have a nice view of your surgical target at all times. And we have rubber bands positioned kind of in a large area. So first thing, before we did anything else, we just had to cut its own tissues. At least we would get this video. You saw some trouble setting up the Zoom this morning, right? It's always hard to make connections like that. So even if we weren't able to make connections, we wanted some sort of activity. Does that make sense? This was stage 1 of our experiment. Stage 2 was teleoperation, where we would control it from the ground. And you saw some of these images before, but we made our own little mission control in our facility in Lincoln. First of all, there's a row of engineers. You can see Rachel here, and she's speaking with the astronauts and Capcom, the Capsule Communications. In the back row is our group of surgeons. Here, waiting his turn. Jobst, who's actually controlling the device. So you can see this. That image is coming from the space station, and he's using the console to control the motion of the robot to actually perform those surgeries. You asked about the latency earlier. Yes, there's plenty of latency. The space station is either 250 miles right above us, but it orbits the Earth, of course. So it orbits in about 90 minutes, and we were operating for about 2 hours. So it was either straight overhead or it could be about 8,000 miles away on the other side of the Earth, of course. So we actually communicated with Marshall Space Flight Center. The signals then went to White Sands, New Mexico, then up to what are called TRISH satellites, which are PhD satellites that are dedicated by NASA. And that leads to all this this switching and this handing off with a lot of extra latency. And then in the back row are the 6 surgeons. We had 6 surgeons who participated in this experiment. These are just general images from the space station up here. Again, this is our image from our robot and our camera. And then this is the loss of signal. There's an S-band and a KU band antenna. We had to be mindful of the loss of signal, that they're not always in communication as they orbit. Here we go. This is our 6 astrosurgeons. And you're going to hear from Dr. Bianco here in a moment. He's from here in Chicago, Los Angeles, 2 surgeons from Nebraska, Houston, and New Jersey. So we wanted a diversity of surgeons that would try the experiment and see if they could all do it. And they were all very, very successful. The latency is not ideal, but it turns out the surgeons just were a little bit slower. And actually, surgeons who have done the same task on the space station with delay or on Earth with the normal system, it takes about twice as long to complete the same task with the latency, but they're equally successful. So we have some preliminary experiments on that, but again, we're waiting for our payload to come back. Here's just a video, Rachel talking on the Capcom, a surgeon controlling the device. This is a surgeon cutting from Earth. Those are the hand controllers that are used to control the motion of the robot. You can see the camera moving there. I think that was Dr. Bianco there. Rachel and I got to sit down and do a little bit. And then there's our experiment on the left there. We had a nice group who made a big shindig out of the whole thing. Dr. Fong was very excited. And then our system has been uninstalled. Astronaut Laura O'Hara and Rachel showed this image. It came down, it's down on Earth. Astronaut O'Hara is also back on Earth. But our experiment is also on Earth. We're waiting for them to ship it to Nebraska. We haven't seen it yet. But I point this out, and Dr. Bianco will talk a little bit more about this stuff in a second. But we just recently, April 30th, maybe May 1st, somewhere in there, had an experiment where we did surgery. We had 4 surgeons in Chicago and 4 surgeons in Lincoln, Nebraska. And we had 2 animals on each side to do practice surgeries with. And we did a total of 8 procedures that day. 4 from Chicago to Lincoln, and then 4 from Lincoln back to Chicago. And this is really where we want to go. Now, on the space station, the latency was again around 600 or 800 milliseconds, pretty significant. But here, between Chicago and Lincoln, it was 15 milliseconds. So really not noticeable. And again, Dr. Bianco can speak to that more directly. But we did several different types of surgeries, from gallbladders to colons to hysterectomy. We did a couple of nephrectomies, removing some kidneys, and it was really quite successful. And we think this has, again, potential for remote locations. Nebraska is a rural state. There's small hospitals in small towns with general surgeons, but maybe they don't do nephrectomies and maybe they don't do colectomies very frequently, just because that's not their patient population. But if you can have a surgeon, an expert, dial in from a remote location and help with a surgery like that, keep that patient local, let them stay home, that could be a big win. And then we'll eventually go back to our military roots and start looking at that problem again. But we think there's a lot of potential. This is all possible because this is small. This is launchable to the space station. This is deployable into small communities and forward environments. Big 8,000 pound, 2,000 pound robots that are 9 feet tall are much more difficult to do that. Actually, the big robot company just introduced a new robot. They bring a semi around to show people the robot. You can hop into the back of the 18-wheeler and see the device. So, the venture is huge. Now, I've kind of talked from the engineering perspective. We're going to have Dr. Bianco now talk about his experience surgical. This is the Museum of Surgical Science with a display on space medicine. So the overlap of those two is us, space surgery. Yeah? You
mentioned the device was to be used 15 times.
Yes.
What happens after that? Is it disposed of or sanitized?
So our FDA approval says it's disposed of. However, we've been doing the testing, and we think we can do up to 4 cycles of 15 times. So you bring it back, basically you throw away all the plastic, all the electronics, but the motors and gears on the inside of this, we've shown can be reused. And so you rebuild a new robot and send it out as new. And that upsets the apple cart of pricing all of a sudden. We think we're cost competitive with other approaches with this, but when this goes from 15 uses to 60 uses, it really changes things a lot. My emphasis with this robot is not that it's small, but it's simple, easy to use. It makes sense to everybody. Everybody kind of gets how it works. And it's easy to set up, easy to move from room to room. Simple, simple, simple is really what we push for. And with that, we think will come, eventually come cost advantages. Yeah?
Excuse me, how big is the port to insert?
So this is about 35 or 40 millimeters. And our clearance is actually for colorectal surgery. And I would only use this robot for colorectal surgery. Your colon is a big organ that has to be removed. You get colon cancer and they need to have colectomy. And so they need a larger incision for that anyway. So the total incision size is less for this robot. During our trial, they would make an incision for this robot, and they would also use that to extract the specimen, and then they'd have just plus one more laparoscopic work.
How do we inflate this space inside?
Pardon me, say that again?
How do we inflate the space inside?
How inflate?
How do you inflate it?
Oh, so there's been experiments. Rachel mentioned what's been done in the past. The only kind of surgery that's been done in space has been small animals, rats. They're used for all kinds of models, and they need to sacrifice them at different points. And so that's the kind of thing that's been done. Nothing like this. Now, on the zero-G flights, where they take the airplane and they fly and they get this, there's been animal experiments for that, and they do insufflation differently, actually. Rather than, they'll have inflatable structures inside the body that will support the abdominal wall and control the organ location. So there's kind of a different approach to that. All that's definitely in the research area, and again, it'll be a while before we do surgery in space. Yep.
The insertion of that, does it go through a sheath, like current endoscopic?
Yeah, so this actually passes, again, with the FDA approval, it passes through what's called a hand assist laparoscopic port, which is just a big blob of silicone that you kind of, it's made so surgeons can stick their hand inside there and kind of help themselves with laparoscopic surgery. That's commonly used in colorectal procedures, again, because you need a hole to bring the specimen out, and we use that for this device. We're currently developing our own port that will simplify that, but yeah. Yes?
So I'm assuming eventually a continuum of the surgeon providing, say, an appendectomy remotely robotically, but then an advanced equipment would be like some sort of AI or automatic pre-program, for example, do an appendectomy. That would be the ultimate.
Yeah,
Is there anything along the continuum?
yes, there's lots of, that's the right word that I always use, there is continuum. So right now, every motion of this, actually, I would go back a little bit. Laparoscopically, everything that's done is done by the surgeon, right? Every little motion. We'll stop the surgeon if they're doing something wrong, right? So we intervene a little bit, but not much. It's mostly just the motion of the robot. Now, on the other side is what you said before. Actually, let me go even further out. My idea was always for a darker problem would be, here's a big blue pill and here's a big red pill. You take the blue pill first, the red pill, that's going to make you sleep. The red pill is actually a robot. It's going to go in, and when you wake up in 14 hours, your gallbladder will be gone. That's the way out there. So somewhere in between those two things. Now, where we will go next, I believe, is more like a horse. So again, picture driving a remote control car around the room. You're again controlling everything that it does. But that's not true when you're on a horse. You kind of give it high-level commands. You kick the horse, we're going over there, go through this gate, but you're not telling it where to put its feet. You're not telling it how to balance. You're not giving it every little detail, and it's figuring out a lot of stuff on its own, but it's taking high-level commands from you. So we've actually used some neural networks to do some things like, just the next simple thing is just touch that piece of tissue, and it will reach out and touch that piece of tissue. And so we've used artificial intelligence neural networks for those sorts of things. Then it's going to be, grab that and cut along this line. And there'll be higher level commands that are issued, and we'll slide along that continuum until we get to more autonomous surgery. Surgeons' jobs are very safe, it'll take a long time. And there's a lot of expertise in there. You know, it's a lot more than, you know, Facebook is very proud about how they can find every picture of me in the world, right? It's much harder to do, even a gallbladder with some unusual anatomy than it is facial recognition and some of these. So it's a hard problem, it really is. We're building a new console, actually, that's just jam-packed with GPUs. I don't know if you guys are any gamers in the room or AI people in the room. They know graphical processing units are kind of machines that make AI possible. So we're going that direction, for sure. Thank you very much.